Everyone, greetings. It is good to have you here back in virtual class. We are in well, basically we're at the final week, which is crazy to think about. So we're going to start by talking about the endocrine system. And the endocrine system used to be called the ductless gland system, but I think endocrine system is a little bit more succinct. So what the endocrine system is, and this is not something we talked about much, but the endocrine system uses signaling molecules called hormones. And if you do take a majors bio class, or if you decide to subject yourself to physiology, then you will learn about signaling molecules quite in depth. But hormones are signaling molecules, and just to tell you what a signaling molecule is, it is a small molecule that is released by one cell or a group of cells that bind to special receptors on other body cells. So what they do is that one cell will release a signal. The signal will go to cells specially designed to receive it, and that signal will tell the cell to do something, either make something, stop making something, so on and so forth. So the effects of signaling molecules are very wide and very diverse. But what they do is that when they connect the cells, then the cell is going to change its behavior in some way. Well, hormones are signaling molecules that travel through the blood and connect with cells. Well, the correct term is bind, but we'll just use connect. And connect with cells that contain specific signal receptors. To give you an example, we can use the hormone insulin. It is released by an organ called the pancreas. There's specialized cells on it called the islets of Langerhans. Well, that's what they were called, but there's been a movement in biology to start naming things by more general names than by the people that discovered them. Now they're known as beta cells. But insulin is released by beta cells, and it connects to other cells in your body, well, basically all of them, and it gives them permission to take glucose from the blood into the cell. Without insulin, there will be nothing to tell your body cells that it's okay to take in glucose, so they will not. And if that's the case, if those beta cells are destroyed or not as effective anymore, then that can lead to a condition called diabetes mellitus. So anyways, if I'm going to show you kind of an example, so I'm going to show you here, I'm going to draw the bloodstream, because hormones, since they are secreted into your blood, in this case, secreted refers to a cell is going to put the signal into its blood. You're going to have a cell that is a hormone secreting cell, which I'll draw here in green. So this is a hormone secreting cell, an endocrine cell. And for teaching purposes, it's going to secrete a signaling molecule that has a specific shape. They do have specific shapes, but not like triangles. So it's going to secrete all of these signaling molecules in the blood. And even though I'm drawing them as being super huge, they're really incredibly small. In fact, right now there's probably hundreds of signaling molecules traveling through your blood. Well, maybe hundreds is a little bit big, but just to give you an idea, there's a lot of them. And I'm going to draw here body cells throughout your body. So these represent the various body cells that you have. And these body cells are going to have different signal molecule receptors on them. So I'm just going to say that this one is going to have a receptor shaped like this. This one's going to have one that is shaped like this. This one's going to have one that's shaped like this. I'm kind of running out of shapes here. Okay. And then we're going to have one that has a receptor that's shaped like this. So what's going to happen is that this signaling molecule is only going to be able to connect with receptors that it can fit perfectly with. If it can't fit perfectly, it's not going to bind. So this signaling molecule, if it tries to bind to this cell, it won't be able to fit and there will be no connection. Same with the green and blue cell. But the orange cell actually is able to perfectly connect with the receptor, and then you are going to have a response of some sort. But the other cells will not have a response because they cannot perfectly bind with the receptor. Think of the signaling molecule as a certain language and the receptor as the ability to interpret that language. So if someone understands German and someone goes up to that person and starts speaking in French, then there's not going to be able to be a connection made because one person doesn't understand the language. It's kind of how cell communication works. So the benefit of hormones is that they're able to cause responses in cells all over the body that are quite far away from the hormone secreting cell. Now, the endocrine system is mainly controlled by a gland called the pituitary gland. And it's actually a system that involves a connection between a part of your brain called the hypothalamus. This purple box will represent the hypothalamus. It's actually more toward the base of your brain. And this gland here is going to represent the pituitary glands. And I'm going to draw the gland like this because it's actually two glands fused into one. And one of those glands is called the posterior pituitary, which is really called the fake pituitary because it doesn't actually make its own hormones. Its proper name is the neurohypophysis. Neuro referring to brain tissue. It's actually an extension. That's not neurohypo. Here we go. It's actually an extension of the hypothalamus. So the hypothalamus actually makes the hormones. So I'm going to draw here a neuron. So you kind of see that it's going to make the hormones in the neuron, and then it's going to secrete them into the neurohypophysis for storage. Now, on the other hand, the true gland is called the anterior pituitary. And it's called the adenohypophysis. And it's called the true gland because it's actually able to make and synthesize its own hormones because it has cells called endocrine cells. Now, the anterior pituitary controls the secretion of most of the major hormones in the body. We're not going to go over them very in depth in this class because that's more of the anatomy thing. But just to give you some examples of hormones, One is called thyroid stimulating hormone, which tells your thyroid to make, well, thyroid hormone. ACTH, which tells your um, adrenals to make cortisol, and we're going to go over the cortisol pathway in class here as our model. We also have follicle stimulating hormone and luteinizing hormone. Those hormones affect men and women differently. In men, it stimulates testosterone and sperm production, and in women, it helps to regulate the ovarian cycle. There's many other hormones too, but we're going to keep it fairly simple in this class. If you want a list of hormones, I put them in the PowerPoint. But you don't need to know them for the quiz and final. You just need to know the cortisol pathway. So anyways, the anterior pituitary, so both of these aspects of the gland have access to the bloodstream. The difference is, of course, is that the neurohypophysis acts as storage. So what it's going to do is it's going to store hormones made by the hypothalamus, where the anterior pituitary makes its own hormones and secretes them into the bloodstream. Okay, now the endocrine system works on a system, well, a system, yes, called a negative feedback system. So I'm going to go ahead and erase this bloodstream here just because we need more room. I'm going to go ahead and erase the posterior pituitary because we're not going to be using it for this pathway. But anyways, what a negative feedback system is, negative feedback system, what it is it is intended, so it involves a series of sensors. Sensors detect levels of things in the blood. Sensors and integrating centers. Remember that an integrating center receives a signal and determines a proper response to keep hormones in a specific range. If you go into the doctor and you have blood work done, you'll usually see a reference range. And if your levels fall within that range, that means that your feedback systems are functioning correctly. If they are not, if you break negative feedback, then it's going to be outside the reference range, either too high or too low. So the idea of negative feedback, I'll go ahead and erase this for now. So the idea between negative feedback and this is not the textbook definition. The textbook definition is negative feedback is something is taken away in order to maintain homeostasis, which is the preferred state of the body. But in this case, I'm going to just change it a little bit. Negative feedback is the regulation of hormone levels by increasing or decreasing the response. So as you'll see when we talk about the cortisol pathway, it is a system that relies on every aspect of the system to do its job. If it doesn't, then the system falls apart. And we'll see that when we talk about the cortisol pathway. But negative feedback systems usually involve something being added or taken away. And I know that sounds weird because negative does mean to take away, but I find it easier to teach, especially at the introductory level, just to say, well, something is added or taken away in order to ensure that the levels um, are within the body's preference. Because if hormone levels are too high or too low, it's going to cause dramatic changes in the body that are permanent and long lasting. Okay, so there is a feedback system called a positive feedback system, which we're not going to talk about ad nauseum today, but it's basically levels keep on increasing and increasing and increasing until they just stop. Think of it as a snowball rolling down a hill. It's going to get bigger and faster and bigger and faster, and then it's just going to stop when it gets to the bottom of the hill. If you want an example of a negative feedback system in something you encounter in real life, is the thermostat. So let's say that you set the thermostat for 68 degrees, I'll just say. Now, if the temperature in the room exceeds 68 degrees, then the AC system will kick in, returning it back down to 68 degrees. If it falls below 68 degrees, then the heater will come on, ensuring that it stays at 68 degrees. That is a feedback system. You are going to constantly adjust the system in order to make sure that proper levels are maintained. Now, let's go ahead and talk about cortisol. So cortisol is a hormone that is received by numerous cells in the body. So it isn't like, oh, cortisol does this, cortisol does that. Well, it does, but it affects each cell differently. And cortisol is a hormone that is usually secreted in response to long-term stress, meaning that let's say that the organism is under a dramatic amount of stress, either through starvation or constant threats or something similar to that. Is what it does is it's going to make pretty semi-permanent changes in the body that ensure that the organism can survive long-term stress. Like, for example, it's going to promote glucose being in the blood, so the cells have access to energy in order to fight the stressor. It's also going to promote fat storage. So what it will do actually is it will start to use your muscles for energy and begin to prioritize fat storage in order to help the organism survive whatever famine they are experiencing. It's also going to do things like it is going to create feelings of anxiety and over alertness, because the idea is that you're in constant bombardment of a certain threat. So people that have cortisol excess, called hypercortisolism, is they actually experience these effects in a too dramatic of a fashion, and then they have long-term tissue breakdown, which I'll go ahead and show you. I'll show you what happens with that after we talk about the pathway. Now in your blood, there's going to be circulating levels of hormone. I'll just draw this as the bloodstream. So we'll go ahead and do these purple dots as being cortisol hormone. And what's going to happen is that the hypothalamus is going to detect levels of cortisol. Cortisol is the active hormone. By active, I mean it's the one that creates the physiological response in the cells. So the hypothalamus has receptors for cortisol. What it does is it sees basically how much cortisol binds with the receptors, and it wants to make sure that only a certain number of other receptors are activated at one time. It's kind of like if you're trying to monitor the number of people coming into a store at once, is you say, okay, well, I only want 2 people to come through the store uh, every 5 minutes. Let's say that we're super social distancing. And if too many people come in, then you're saying, okay, well, it's time to slow it down. If not enough people are coming in, it's time to let more people in. So, anyways, the hypothalamus is actually not capable of, making certain hormones. So, what happens is that it is going to send a signal to a gland that's actually the size of a pea called the anterior pituitary, also known as the adenohypophysis. And the anterior pituitary makes its own hormones. And these hormones are called trophic hormones. But anyways, one of the hormones made is called adenocorticotropin hormone. You don't need to know the exact name of that. We'll just call it ACTH, its proper abbreviation. So what's going to happen is that depending on the levels of cortisol, the hypothalamus is going to send a signal to the anterior pituitary called CRH, or corticotropin releasing hormone. This is a special hormone that only is received by the pituitary. There's actually a special system that we won't get into. It's called a portal system that connects the hypothalamus directly with the anterior pituitary. So it is like a direct pathway. Now, depending on the levels of CRH, the anterior pituitary is going to release a hormone called ACTH, as we talked about. And ACTH is received by a gland called the adrenal gland. So it's found on top of the kidneys, actually. It's kind of shaped like a hat. And amongst other things, the adrenal gland is going to receive ACTH, and depending on the amount of ACTH received, is going to secrete cortisol into the bloodstream. The hypothalamus is going to detect the levels and adjust it accordingly. So just to show you how it works, if we are going to do a flow chart here, is the hypothalamus is the first step in the pathway because it acts as the sensor. And the sensor, what it does is it receives or it detects levels of things, and then it is going to determine the proper response. Now, on top of being a sensor, the hypothalamus is also an integrating center, which means that it determines it determines an action that will restore this or that will yeah. So let me think about putting this in clear ways. So the integrating center receives a signal and determines an appropriate response. Now, in this case, the hypothalamus secretes a hormone called corticotropin releasing hormone, which we'll call CRH. And CRH is received by the pituitary. So this is the hormone. It is received by the pituitary, and the greater the CRH, the greater ACTH. Okay, but anyway, CRH is going to be received by the pituitary, and the pituitary is not a sensor as much as it is an integrating center, because it is going to receive the amount of CRH and it's going to adjust its secretion of ACTH accordingly. So it's going to release ACTH, which is only received by the adrenals. And as I said, is the more CRH is secreted, the more ACTH is secreted. And that's going to be true with cortisol. So I'm going to have to continue the pathway here. So the adrenals are called the target because the target is what is going to secrete the active hormone. So the target secretes cortisol, which is the active hormone. So to kind of clear this up, only the pituitary has receptors for CRH. Nothing else does. Only the adrenals have receptors for ACTH. Nothing else does. But cortisol is the active hormone because it binds with several, many cells in the body. So without the adrenals, ACTH can circulate in the blood all it wants to, but it's not going to have any response. So the hypothalamus acts as the sensor because it detects levels of cortisol, and it acts as the integrating center because it's going to secrete the hormone CRH, which is received by the pituitary. The pituitary receives CRH, and depending on the amount of CRH detected, it's going to release a corresponding amount of ACTH. It's called an integrating center because it determines a response. ACTH is going to bind with the adrenals, which acts as the target, and it is going to secrete cortisol. The amount depends on ACTH. So let's go ahead and do a simple pathway now. Oh, and I should also mention that the changing levels of cortisol act as what's called the stimulus. And the stimulus is what kicks a feedback system into action. So anyways, let's say that the hypothalamus detects that cortisol is too high. Well, it is going to lower its secretion of CRH. The lower levels of CRH will be received by the pituitary, which will lower its levels of ACTH. As a result, the adrenals will receive the signal of less ACTH, and it will decrease its secretion of cortisol. And the cycle is going to rinse and repeat. So kind of just to show you again here, cortisol is received by the hypothalamus. The hypothalamus secretes CRH, which binds with the pituitary. The pituitary, depending on the levels of CRH received, is going to adjust its secretion of ACTH, and then ACTH is going to bind with the adrenals, which will then secrete a corresponding amount of cortisol. But as you're seeing here, is each system is dependent on the prior system in order for proper functioning of the system. It's kind of like a factory that's building a car. Is that one person is depending on the other person in order to do their job correctly, or the car will fall apart. That's called a recall. Why am I writing adrenals? This is the pituitary, just to make sure everything's nice and labeled. I'm not going to go into this too in depth, but feedback systems can fall apart. Sometimes tumors can form on the pituitary that cause it to malfunction and secrete too much hormone. So in a case like that, is that there's a tumor that forms on the pituitary, which is actually fairly common. It's going to ignore whatever signal it gets from the hypothalamus. It doesn't care. It would just secrete as much ACTH as it wants to. Since the adrenals, they just go by whatever signal they receive, is they're going to get the huge amount of ACTH. Make this clear. And in response, they're going to pump out a huge amount of cortisol. And the hypothalamus is going to say, whoa, that's way too much. It's going to send a signal of CRH to tell the pituitary to slow down its ACTH secretion. But this tumor has taken over, and it's basically decided that it's just going to release as much ACTH as it wants to. So you're seeing here that the feedback system is going to be broken down because one step in the process has malfunctioned. So cortisol will never come down, even though the hypothalamus is desperately trying to tell it, hey, this needs to slow down, but it's not. To show you some examples here. So let's go to our browser. And let's do Cushing disease. That is the disease that is correspondent to excess cortisol levels. These are the symptoms associated with it. And the reason why there's so many symptoms is because all these cells in the body, the muscular system, the integument, reproductive, skeletal, cardiovascular, neurological, they all have receptors for cortisol and they all respond accordingly. And these are some more symptoms. So you're seeing that the effects on the organism are widespread. Also, there is acromegaly, which is caused by excess amounts of growth hormone. So when the organism is younger, well, I should say person, when the person is younger, they have extreme growth, but as they get older, then when they cannot grow anymore because their growth plates are fused, their bones just start to get bigger, and everything gets bigger, including their organs, which is why they have shortened lifespans. But there are procedures to stop this. They can actually go in if they detect the tumor and take it out, which will stop the growth hormone excess. One such person with acromegaly was Andre the Giant, the famous wrestler of the 80s. He was also in the film The Princess Bride. Huge man, absolutely huge man. About 7 feet, probably 450, 500 pounds. One of my favorite pictures is from the set of Conan the Barbarian. So Andre the Giant and Wilt Chamberlain, the legendary basketball player, next to Arnold Schwarzenegger. And Arnold Schwarzenegger was a huge man, or is. 6'2", probably about 230, 240. And Wilt Chamberlain and Andre the Giant just dwarf him. I mean, he almost looks like a toy. And here's another funny picture. But you're seeing that Andre's physical features are larger. In fact, everything is larger, including his liver, which was good because he was actually a raging alcoholic. Like, he was known to drink like 140 beers at one time. Yes, cans of beers. So having that larger liver probably helped him survive that. This is him on an airplane, well, seats. That's also him with a 12-ounce can of beer, about the equivalent of a 12-ounce can of soda. You're seeing how small it looks in his hand. Great guy, but also miserable because he just wanted to be normal. And um, and because he wasn't, he was actually pretty miserable, sadly, despite his fame. Once he was at a bar, which was his favorite establishment, and he was drinking, and a group of guys started to make fun of him. And at first he just sat there, kind of ignoring him. Then he got really mad, stood up, chased them out of the bar, and they ran wisely. They got in their truck, and Andre the Giant went up to their truck and tipped it over. Now, keep in mind, 80s trucks were not the size that they are now, but still, the fact that a man could tip over a truck with 4 adults in it is fairly impressive, I would say. Okay, well, I hope you guys enjoyed this lecture on the endocrine system. Next up is immunity.